Dear Mr. Chairman, ladies and gentlemen, thank you for possibility to present our results from area of additive manufacturing materials. This is our contribution from Slovak University of Technology in Bratislava, from my company, from my group, research group, and this research is resulting after cooperation with University of Pilsen, Mr. Miloslav Kepka, which we will have presentation. Mr. Kepka will have presentation next day. Analysis of this aluminum alloy at the beginning. Short content of my presentation. Specification of this alloy. Then influence of build orientation on static and also cyclic properties. Then comparison of cyclic properties in tension versus properties in torsion, alternating torsion. Then comparison conventional and casting, conventional casting and additive manufacturing materials, and then some conclusion. I try to enlarge not only for this alloy, little bit generalized. The process of origin of AM material is rather different, like a process of origin of conventional casting. Conventional casting, this is the liquid phase, and very slowly become to the first crystal and to the solid phase. Opposite processes in additive manufacturing. This is solid phase, all around is solid phase, and very small melting pools are in the liquid phase. And from this results, from this different condition of origin, resulted different microstructure, and different microstructure lead to the different properties. This is not conclusion, this is only beginning. This is the outcoming from these two different processes. On the left, this is the conventional casting, these particles, magnesium, silicium particles, like a chain. And on the right, this is the melting after melting process after this additive manufactured process. Different microstructure. Down is the composition, chemical composition of this alloy. This is the well-known alloy and very well used in industry. First part, comparison in static properties. This is the tensile diagram between the casting alloy and the additive manufactured alloy. This, for me, is relatively surprised, but is relatively often in this type of technology. Additive manufactured curve is over the casting. Conventional casting. Is necessary to mention that this material, both these materials are the state without the heat treatment. This is in build, yes, without the heat treatment. That higher strength after AM process and also higher ductility is possible to see from this diagram. Interesting is this comparison in orientation of additive manufacturing process. Yield stress not so significantly different from this orientation. Also, ultimate stress also not so significantly different, but the ductility here is significantly different. I try to explain in the next slide. That this is the anisotropy in static loading is relatively not interesting, not important for engineering calculation. In properties, in cyclic properties, this anisotropy is well known. This is the first diagram from our testing specimen. This is the comparison between the horizontal oriented building process. This is this blue line, and this down line is from vertically oriented process. This is the horizontally oriented process. This is the vertically oriented process. This difference is significant, not so much, but it's significant. This difference is about 10% in area of stresses or amplitude of stresses, but in the area of number of cycles, this is 2 or 3 times. That is significant, this difference. Also, these differences depend on the type of AM material, because in other material, for example, this is the merging steel. This difference between the orientation, build orientation in fatigue properties are relatively not so much significant. Is a little bit different, but not so much significant. That depend of some other factor like a ductility of materials. If this anisotropy is so significant or so small significant. This differences is resulted from defects. I select two defects. This is microstructure of this aluminum alloy. This defect is relatively very friendly for fatigue, relatively, because this shape and this curvature lead to the relatively small stress concentration factor. If, for example, crack go through this leg of fusion, is possible to say, tip of crack have theoretically infinity stress concentration factor, and when go through this defect, probably stop, because this ratio decrease this infinity stress concentration factor. Bad defect is this very sharp, this tip of this defect is very sharp, and this is this problem for beginning of crack and also for propagation of crack. That this type of defect and orientation this defect into the maximum stress, normal or shear, this is this very interesting things. Here is only for documentation crack path, and here are the defects. Probably not affect this defect, this crack path, because this is this friendly defect. It's possible to say friendly, yes. This defect in this aluminum alloy are distributed in all cross section. This is the boundary. This is the shape of boundary. Many defects. Different orientation of building. Inside is also different orientation of building. These defects are also on the outside surface. If you turn the surface, also are here these defects. These defects have dominant influence of this fatigue lifetime. It's are present here. Now comparison between the tension and torsion, and between additive manufactured and between the conventional casting. These two are in tension compression, R-1. This is the AM material, this is the casting, and this is the in torsion, also AM material, also casting. Here is not possible to see the comparison. Comparison is in one same diagram here. Now this is the interesting, this comparison. This green line, this is the tension. This green line, this is the torsion line, are parallel in tension. Okay, in tension, in torsion. In additive manufacturing, that is this blue line and this dashed blue line, this is for additive manufacturing. Okay, that this once again green is conventional casting and blue is additive manufacturing technology. And problem is this parallel. We are often in conventional steels, conventional metals. This parallel is often. In additive manufacturing, is this not parallel line in tension, in torsion. This is new behavior, which is not so often in conventional area. Also, another steel, this is Margetin, also have non-parallel tension versus torsion. But exist also additive manufacturing. For example, this is the inox steel, which have parallel. That more often in additive manufacturing technology is this non-parallel tension torsion. This is lower offer this situation. I try to explain this not parallel. This not parallel have or caused big problem in calculation, for example, multi-axial fatigue in engineering stage, because when we have ratio between the fatigue limit in tension and fatigue limit in torsion, this ratio is not the same if this line are not parallel. Okay, that this multi-axial criterion is not functioning right if have this ratio. We have from our university this different criterion in which is here the slope, not fatigue limits, but slope. And this slope is good functioning for this unusual behavior between tension and torsion. Also, it's possible to explain here on the Mohr circle. This is the pure tension. Pure torsion, pure tension. If the amplitude is the same, it's this Mohr circle same, but different orientation is when we control it torsion. Alternative torsion, this is this controlling process of stress. In tension, this is this orientation of controlling process. That this is different plane in which is maximum shear stress, in which is maximum normal stress, and the orientation of this this maximum normal or shear stress in comparison with defects. This is this reason why this line in torsion and tension are not parallel. This is one of the reasons. And second thing is also ductility. If this material is ductile, these differences will be smaller. If it's low ductile, will be low. Okay, comparison between the additive manufacturing and conventional technology. This is this additive manufactured specimen, horizontal building process, vertical building process, documented as a preview slides. And this is the conventional casting. All materials are without the treatment process, heat treatment process. That also is possible to say this difference is relatively high. In area of cycles is 1 order. Also, differences between this line and this line in area of lifetime is over that 1 order. This is big difference. And possibility of additive manufacturing is this technology increase this line until this. It's possible to obtain by better technology and orientation of building, but this is also very complicated because this orientation of building depends on the shape, depends on the supporting and other things which you know from this additive manufacturing technology. But this is the maximum what is able today. For engineers, we must consider this line for calculation, and both these lines are very long distance from this conventional. That cyclic properties are rather lower that in additive manufacturing processes in comparison with conventional casting. That it's possible to summarize the specifics of additive manufacturing materials from point of fatigue life for cyclic properties. Exist 20 parameters when you set the printer for the obtain this specimen, but these 4 is possible to say are significant for fatigue lifetime and for cyclic properties. Anisotropy is first during this build process. Second is this internal defect and orientation of this defect in comparison with the main stresses. This is very interesting, important. Also surface layer, and then this not parallel line in tension and torsion. This is a very big challenge for create new multi-axial fatigue criteria. And generally it's possible to conclude that are defined these 4 interesting or 4 most important differences or specifics of additive manufacturing. Once again is here. Second conclusion, it's possible to say that current level of additive manufacturing technology cannot achieve the cyclic properties of conventional manufacturing. This is the challenge, but probably will be very, very long time lower that conventional. It depends on this defect, what I mentioned, defect and orientation of defect into the maximum or main stresses. Also, it's possible to say that fatigue strength of AI materials is sensitive to the orientation of shape of defect. Yes, I mentioned it. And what is very required is higher order of standardization of AI materials, because now are in process another test with the same specimen, with the same material, but from different producer, different supplier, but same process, same machine, but different supplier lead to the different properties. This is not possible in conventional casting. And also the test in area of multi-axial fatigue also lead to the very big problems that very required is the way for more standardization of AM technology of manufacturing. This is last slide of my presentation. Thank you for your kind attention.
Okay, there is time for one question. Are there any? Okay.
Hello. Regarding conventional casting, are you talking about high pressure die casting?
No high pressure. Conventional, no high pressure casting.
Okay. Gravity casting.
Yes.
So
Low
less
pressure casting is possible to say.
Okay. Thank you.
This is not from bicycle frame, because in bicycle frame it's necessary to high pressure casting.
Yeah.
This is conventional big particle from which we turning this specimen.
Okay, because otherwise you also have a lot of defects in high pressure.
Yes, but this conventional casting, if it's the big body,
Okay.
is not so big problem with defects in conventional casting.
Thank you.